Hello students, in this video we'll discuss the singular value decomposition of an m by n matrix. Let's let A be an m by n matrix, okay? And then if it's not a square matrix, I can't diagonalize this matrix, so I need some other mechanism to extract spectral properties of the matrix A. So to do so, we're going to do the following. We're going to consider A transpose A, which will be what? This is going to be, this is an n by n symmetric positive semi-definite matrix. Okay, that's easy to see. So we can easily verify that that matrix A transpose A is going to be symmetric, because if I look at A transpose, that will be A transpose transpose, which is just A transpose A, right? And then if I look at A, if I look at X, A transpose A with the vector X out in front of it, a vector X over here, then what this is over here with a transpose, of course, this is just going to be the norm of AX quantity squared, which is greater than or equal to 0, right? So in other words, it's symmetric and it's positive semi-definite. Symmetric and positive semi-definite. Great. Now I can apply the spectral theorem. So by the real spectral theorem, there's an orthonormal basis phi 1 hat through phi n hat of eigenvectors for A transpose A. Corresponding to eigenvalues which I will arrange in the following order. Lambda 1 bigger than or equal to lambda 2, bigger than or equal to all the way down to lambda n. And we know that since the matrix is positive semi-definite, the eigenvalues are all non-negative numbers, right? So these are all greater than or equal to 0, okay? And so what we're going to do now is now we're at a juncture to define what the singular values are. So define the singular values of the matrix A. Remember that A is an m by n matrix, right? Are the square roots of these numbers lambda, right? Are square root lambda 1, square root lambda 2, square root lambda n. And we're going to write all these things just as numbers sigma 1 through sigma n. So here, of course, sigma I is just the square root of lambda I, okay? So those are the singular values of a matrix, okay? And we're going to, over the next couple of videos, we're going to really try to understand the properties of these singular values and see how the matrix A treats these singular values, okay? Great. And so now we want to continue on with our analysis. And so now the question becomes is this. Well, one sort of bit of information we want to extract from this is the following. Let's let R be the largest number such that lambda R is not equal to 0, right? And so what that will mean is that means that R over there, that's the largest one such that lambda R is not equal to 0. So that tells us automatically then the rank of A, which is the same as the rank, we proved this in the previous video, of A transpose is going to be equal to R, right? And so now what we're going to do is, in some sense, with the first of these R vectors over here in this orthonormal basis, phi 1 through phi r, give me almost all the information I want to know about the matrix A, right? The rest of the information is contained in the null space of that matrix, okay? So that's R. And so what we're going to do now is we're going to define for 1 less than or equal to j less than or equal to r, some new vectors over here, psi j, which is going to be A of phi j hat over sigma j. Now in this range, we know that those sigmas are not equal to 0, so this is perfectly well defined in this range. Now, what's the cool thing about these vectors phi j? Well, now let's look at psi j dot product with psi k, like that, okay? Well, this is going to be a 1 over sigma j sigma k, and then I'm going to have an a of phi j dot a of phi k, like so. But now what do I know? I can put the transpose over here. So what we're going to do is we're going to take the transpose and the dot product. I can take that and put the transpose over here. So it becomes a transpose a. And so this becomes 1 over phi j sigma k. And then phi j hat dot what? A transpose a phi k is exactly equal to sigma k squared, because that's the square root of those things over there, times phi k, right? So one of the sigma k's is going to cancel out. And of course, these are an orthonormal basis. So what this is over here is this is going to be delta jk. So this is sigma k over sigma j, delta jk, which of course just reduces when j is equal to k, that prefactor cancels, so that's just delta jk. So this set is actually an orthonormal set, right? And so this set is orthonormal. So I can replace these are really equal to psi j hats. Great, okay? And so now what's the really nice thing? So I'm going to write down this formulation so I know that this tells me, this relationship over here tells me, gives me this important formula that a of phi j is equal to sigma j psi j hat. And this is the basis of our singular value decomposition. With one sort of catch over here, and that catch is that I may not have got enough of these vectors. So of course, this is an orthonormal basis of Rn. But of course, since I'm going only up to what? This definition only works for j between 1 and r. But what I can do is I can take this orthonormal set psi j. So in other words, what I want to do is I want to extend psi 1 hat to psi r hat to be a basis, an orthonormal basis of Rm. Just by Graham-Schmidt, we can do that. Up to psi r, and then psi r plus 1 is the new one, all the way up to psi m over here. Going to send an orthonormal basis. Great. And so now what do I know? Well, what can we say? We can say the following. We can say that this matrix relationship over here says, let's look at our matrix relationship. Our matrix relationship is A phi 1 hat all the way down to phi r. I can put a whole bunch of extras in here, phi r plus 1, all the way down to what? All the way down to phi n. Well, what's this going to be? Well, the first r of them are going to be what? The first r of them are going to be sigma 1 psi 1 hat, all the way down to sigma r psi r. And then I can just put in zeros for the rest of them. 0 psi r plus 1, all the way down to 0 psi m hat over there. Because the rest of those things are just 0, right? So if I 0 with the vector over there, I'm just going to get 0. So all these things over here are really just 0. I just fabricated a whole bunch of zeros into this factorization, right? Those are all just 0. Those are all just 0 columns over there. And now, of course, I can write this in matrix notation. In matrix notation, this says that A applied to the matrix phi capital, which is the matrix of all these, this basis over here. So if I put these into columns, I'll have a matrix phi that contains whose columns are just the phi 1, phi 2, to phi n. Is going to be equal to this matrix psi over here, which contains the what? Contains psi 1, psi 2, psi m in the columns. And then this diagonal matrix over here, sigma 1 through sigma r, that's an r by r identity matrix, and then zeros in these other blocks over here, like that, okay? And so we'll call that matrix over here sigma. And now since phi is orthogonal, I can put the transpose on the other side and conclude that A is psi, the vectors that come over here from this definition extended to an orthonormal basis. Then this matrix over here, sigma over here, and what is this matrix over here, sigma? It's an r by r matrix in the top left corner that contains the singular values, the non-zero singular values on the main diagonal. And then you have what? This matrix over here has to be an m, so this of course is a m by m. That's an m by m matrix. This is an M by N matrix over here. And then this matrix over here is an N by N matrix. N by N matrix over here, phi transpose over here, right? And so the result of this combination over here, and so this M by N matrix over here, like I said, has an R by R diagonal matrix in the top left corner, which contains all the non-zero singular values, and I put zeros everywhere else in that matrix to make the dimensions balance out. So that's the key features, that this is an R by R matrix with non-zero singular values up here, and that tells me exactly what the rank is going to be. So this factorization over here is called the singular value decomposition, the SVD, singular value decomposition. And the singular value decomposition is valid for all matrices which are M by N matrices, because I can pass from an M by N matrix to A transpose A, which is a positive definite self-adjoint matrix, and I can use the spectral theorem. I can use orthogonal diagonalization on that symmetric positive definite matrix to find out what these singular values are, and then I can find the corresponding right and left singular vectors, the psi and the phi matrices over here, to construct this singular value decomposition. Thank you very much.